Hey everybody, so we're just about ready to wrap up our almost last unit in Chemistry 1 here. So we've been looking at all kinds of different stuff here in Chapter 15, a lot of it relating to different types of reactions, especially about solutions. So this very last bit that we're going to do here is to take a look at what happens for reactions with solutions. And basically this first part of this video here is going to take a look at precipitation reactions, where we're taking two solutions together and forming a solid. And then the second half of this is going to take a look at what happens when we react two special kinds of solutions, acids and bases, together and form liquid water. So that's the next video after this one. So this one's all about dealing with precipitation reactions. So this video is going to have quite a bit of review in it as well about kind of how to do double displacement and use solubility rules and some of that kind of stuff. So should be a good review. And then just that last part about how to kind of do that stoichiometry part. It's very similar to the stoichiometry we've all done. Your final exam's coming soon, so maybe this will help. Anyway, there you go. That's what we've got today. Stoichiometry, dealing with precipitation reactions for solutions. Okay, so start it up. Just as a reminder, what we're talking about here when we're talking about precipitation reactions. So this is when we've got two different solutions that we've got together, and they usually are both clear liquids to begin with, aqueous solutions, right, dissolved in water. We combine the two solutions together. Sometimes something happens, and we usually tend to talk about the ones where something happens because it's more interesting, but a lot of times we get the formation of some sort of a solid, like the pictures that you see on your screen. We tend to pick really pretty ones for a Chem 1 class because it's more fun to look at those. But in terms of what's going on here, we got to kind of think back to what's happening in solution. So remember, in solution number 1, we had some ions that were present. In solution number 2, we had some more ions that were present. And we dumped them all in the same container. Sometimes some magic happens between some of those pairs of ions where they are so strongly bonded to each other that they form this sort of insoluble product, this solid, that then falls to the bottom. And it looks cloudy at first, but eventually it'll settle out to the bottom. So typically with these, what we've got to look at again is that difference between what's happening with those ions. Are they attracted to one another, or are they more attracted to the water that they're in? If they're more attracted to the water, they're soluble, and the water molecules, because it's polar, pulls them out into solution. If they're more attracted to one another, or more strongly attracted to one another, then they're going to form that solid. And we call those solubility rules. This is how we figure out what that sort of attractiveness ratio is. In terms of figuring out what they are, these are always double displacement reactions that we're dealing with here. Precipitates can be formed other ways as well, but for a Chem 1 class, double displacement. Two partners are switching with one another. The cations and anions are going to find a new partner potentially and see if there's some sort of interesting attraction that's going on there. Remember, when you're writing your equations, we'll do some practice here in a second, don't forget that those ions don't change. So the ions themselves stay the same. So if it was copper 2 to begin with, it's still copper 2, or if it's sulfate, SO4 with a 2- charge, it's still sulfate afterwards. Those ions don't break up. When you're trying to figure out what your new products are, we talked about using the first name, last name kind of switch, that, partner A and C go together and B and D go together, inside, outside. But don't forget, when you're writing your new products, that you've got to think about what those new charges are. Don't forget to balance your charges, and then at the end, you've got to be able to write that final balanced equation for it. I'll remind you to get a solubility rules table out if you want to use one to practice. We also have that shortcut, the Nakel-Noso rule, that says most things that contain either sodium in its family or chlorine in its family or nitrates and sulfates tend to be soluble. It's a good shortcut rule. And again, keep in mind that when you're looking at solubility rules, the word insoluble means it's forming a precipitate. That's the good stuff that we're looking for. Those are strongly bonded to each other. Soluble means it's in solution, it's dissolvable. Don't think of it that way. And those are the things that are not really reacting, they're just the spectators. And then finally, keep in mind that if you have two things where both of your new possible products are soluble, that's really no reaction. They were soluble to begin with, soluble afterwards. Call that just friends in class. So let's take a look at a practice example of this, because it's a little bit easier to talk about a real example than sort of the generic rules on this one. So this particular question is talking about how we actually form bone, the material that bone is made out of, the hard stuff. We can make this from a simple double displacement reaction between two compounds. The compounds are sodium phosphate and calcium chloride. So number 1, write the balanced equation for this reaction, and then number 2, figure out what the chemical name is for the mineral. So this is a practice problem. You really should be able to do this on your own, but take a second and figure out what they are. By the way, phosphate is a PO4 with a 3- charge. Probably don't remember that off the top of your head. And then the other ones you should be able to write it. So hit pause right now, grab a piece of scratch paper, see if you can write out the balanced equation for the reaction between sodium phosphate and calcium chloride. Okay, so I'm about to go on. Hope you had a chance to figure out what it was. So here's sodium phosphate and a 3PO4. Remember, sodium is a 1+, and phosphate is a 3-. Phosphate's PO4. The second thing is calcium chloride. Calcium's a 2 plus and chlorine's a 1 minus. That's where that little 2 comes from in there. And then they're going to switch partners. So we're going to have the sodium and the chlorine are going to come together, so the outside two. And then that's going to form sodium chloride. Sodium's a 1 plus and chlorine's a 2 minus. Remember, those subscripts disappear because those were only there from balancing charges in the left side of the equation. Okay, so our other product is going to be calcium and phosphate. And again, we're going to try to write that product. Now we've got some new subscripts appear in this one. Again, those are due to balancing charges. That's where those come from. Calcium's a 2 plus, phosphate's a 3 minus, so you cross them down. So you have Ca3PO4, crazy looking thing. Then we use our solubility rules to kind of try to figure out what's what. Sorry, got to balance our equation first. Take a second to do that. Ca3PO4 was my most complex molecule that was on there, so I balanced the left side to match that. I needed 2 phosphates on the left and 3 calciums on the left. And then I know after I kind of finish that part of doing my math, I'm going to need 6 sodium chlorides to get my equation balanced out. So now I have a complete balanced equation. Lovely. And then here's our solubility rules. Nacl-NoSo says that sodium chloride is soluble. You know sodium chloride is soluble. And then we've got the Ca3PO4. That's got to be our solid. And again, if you have a solubility rules chart in front of you or something like that, you'd see that most phosphates tend to be insoluble. So that's got to be our solid, our precipitate. And that's actually what bone is, calcium phosphate. So there's our name of that particular material. So you've got to have this as a basis to do some of your double displacement reactions. So we could figure out, for example, how much calcium phosphate could be formed from a particular reaction. It's stoichiometry. It's back. So how do we do this? Remember, it's been a while, but it's coming back. It's all back around, man. This class is so circular, right? Cyclical. So kinds of questions that we can ask in terms of stoichiometry now that we have a balanced equation. For example, how much precipitate did we get? How much calcium phosphate was formed? Or we could ask questions like, how much of these solutions do we need to form a particular amount of something? So this is stoichiometry. And remember, as a review, what is stoichiometry? Number one, we have to have a balanced equation because that's going to give me the mole-to-mole ratios between any two compounds in that reaction. They could be 2 reactants, they could be 2 products, they could be a reactant and a product. But that balanced equation is the gateway. It gives us the mole-to-mole ratios, and that's the central step of every stoichiometry problem that we do. Sometimes we do a little bit of fancy stuff to go from, say, grams to moles to get in or moles to grams to get out. But that's always the central step, is that moles to mole step. Example number one, we could do, say, for example, determine the amount of product that's formed, how many moles of product. That's usually precipitates what we're concerned about, so that'd be one way we could do it. Second thing we do, and you'll see some examples of this, how much of the second reactant do I need to use up a reactant? So I've got this much sodium chloride, how much of the other stuff do I need to use to get rid of it, or something along those lines. So those are the kinds of examples that we can do, and those are the problems that we're going to work out next. Here we go. So here's example problem number one. How much calcium phosphate could be formed from 100 milliliters of 0.5 molar calcium chloride solution? Now this is the same balanced equation that we had before. I put it back up on the screen here so that you can use it. You don't have to go rewrite the equation. So here's our series of steps. This is the problem solving situations that we always do when we're doing the stoichiometry problems. Number one, we've got to use that mole to mole step to convert from A to B. In this case, my A and my B are calcium phosphate and calcium chloride. Those are the two chemicals that I'm concerned about. You got to figure out which ones we care about. Number one, the second thing we have to do after that, number one. Number three, B, I don't know. The next thing that we need to do after we know what that central step is we're going to have to go figure out the number of moles of compound A that we have. The only thing that's different in this chapter versus previous chapters is that here we're given information about the concentration of a solution as opposed to the grams of something. So we've got 0.5 molar calcium chloride solution. So we're going to use the molarity equation to deal with that. And then the last thing that we're going to do after we do our mole-to-mole ratio is that we're going to convert the moles of compound B back to grams. And we've done that before a bunch of times. That's just using molar mass. So again, really the only difference between what we're doing in this chapter and what we've done previously is that we have to use molarity to get the number of moles of our particular starting compound as opposed to molar mass. So let's take a look at how we work this out. You may want to grab a pencil, paper, and try it on your own, but I'm going to do this myself to make this thing. All right, so here we go. Let's take a look at using those steps to try to figure out how to attack this particular problem. So we're trying to figure out how much calcium phosphate we can form from using or starting with 100 milliliters of 0.5 molar calcium chloride solution. So the first thing I do when I attack these problems, I start to identify, all right, what are the two compounds that I'm actually worried about in this problem? So the problem says how much calcium phosphate. So I actually go through this process. Circle that one. Okay, calcium phosphate, I need to know that one. And it's how many grams. That's what how much translates as. And then the other thing that's discussed in the question is that calcium chloride solution, CaCl2. So there's that one. That's the other one I'm going to need to deal with. And there's the information that I have about that from the problem. I've got 100 milliliters of it, and it's 0.5 molar solution. So now at least it's easier to see. I'm going to have to do my mole to mole ratio from calcium chloride to calcium phosphate. So it's a 3-to-1 ratio. So I need to figure out how to get to moles now as the next step, right? So the next step is I'm going to use this information I have about molarity to deal with the other pieces of that to figure out how many moles I've got. So this is the first step that I need to do. I'm going to use that information, calculate the number of moles that I've got of that stuff, which is the molarity part. And then the next thing I'm going to be able to do, again, is that mole to mole ratio. That's our central step that we do every time. And then the last thing is I'm going to figure out how much calcium phosphate, which is that last piece, converting from moles back to the number of grams using molar mass. So this is kind of the rhythm that these particular problems take. It's very similar to the ones that we've done before. We just don't start with a grams to moles step. We start with a molarity to moles step. So here's my calculations. So I'm using this information over here on this left. Here's my molarity information. I've got 0.5 molar equals the number of moles, which is what I'm solving for, divided by 0.1. Remember, you have to put it in liters, not in milliliters. So that's the move it over 3 places, decimal places. And I end up with 0.050 moles of calcium chloride has to be present in that solution. Now the next step is to use my mole to mole ratio. So here's my little tiny wonder fraction. I'm starting with 0.50 moles of calcium chloride, and they're in a 3-to-1 ratio, and those numbers again come from the balanced equation. 3 moles of calcium chloride, because that's the coefficient right here, to 1 mole of calcium phosphate over there, and that's what goes up on the top. So that means I could produce from this 0.0167 moles of calcium phosphate. Again, it's multiply across the top, divide by the bottom. And then the last step is to convert from that number of moles back to grams. So here's my last little molar mass step over here. Molar mass of calcium phosphate, it's a big number, 310.18. And again, that's that moles to grams step. 3 calciums plus 2 phosphoruses plus 8 total oxygens is 310.8. So I multiply across the top, divide by the bottom, is 5.2 grams of calcium phosphate. And that's my answer to this. I could have done, just so you know, if you like to do this, I could have done these two things in a single wonder fraction all the way across. I did not have to break it into 2. But it's up to you which one you want to do. If you want to do it as moles and then moles to grams, that's totally fine. So my final answer, 5.2 grams of calcium phosphate could be produced from this. Okay, your turn. Take a second, see if you can practice this out. This is kind of the second example. Trying to figure out how much sodium phosphate would you need to precipitate out all the calcium ions excuse me, from calcium chloride solution. Say a different molarity here, so you have to slightly do your different math, but this is a really good spot for you to take a pause. See if you can figure out how to do the molarity part, and then the moles to moles part, and then the moles to grams part. So go ahead and take a second and figure out what this one is. I'm going to move on, so you should pause and do it. Did you pause? Okay. So here's the two things I'm concerned about. Again, I'm applying my kind of problem solving. It asked me about how much sodium phosphate, so I'm going to circle that one and do the question mark grams. How much of this do I need? The second thing is I've got information about all the calcium ions from calcium chloride solution, so that's why I circled that one. And then there's the information I have about that solution. So I'm going to use my same sort of problem solving steps. The other two things, yeah, they're present, but I don't really care about them in this particular problem, so I can kind of ignore that they exist. So the first thing is I'm going to figure out how many moles of calcium chloride I have. So then I can do the second step, which is the mole to mole ratio. And then the final step is I'm going to convert back from moles to grams for our final product. So here we go. Here's my information about molarity right here. I've got 0.3 molar solution, and I have 250 mils of it. And 250 mils, move the decimal place over, it gives me 0.250 liters. So by the time I solve this out, just check your algebra, it's 0.075 moles of calcium chloride. And now I can do my mole to mole ratio. That's the second kind of phase of these problems. So here's my little mole to mole ratio, my mini wonder fraction. These are in a 2-to-3 ratio, and again, those numbers come from my balanced equation. 2 moles of sodium phosphate go with 3 moles of calcium chloride. So when I math that out, 0.075 times 2 divided by 3, I get 0.050 moles of sodium phosphate could be produced. And then the very last step is to convert from the moles of sodium phosphate to grams. So there it is, moles of sodium phosphate to grams. This number up here is the molar mass of sodium phosphate. Again, that's 3 sodiums, a phosphorus, and 4 oxygens all added together to give me 163.94. And then, oops, sorry about that. And then we get the total of 8.2 grams. So kind of that typical rhythm here is that you're going to use a molarity to moles, and then you're going to do moles to moles, and then finally you probably do moles to grams. Those are the 3 steps that we do when we're dealing with solutions stoichiometry problems. It's not too bad, actually, very similar to the ones that we've done in the past. So here's our review. Stoichiometry and solutions, again, these first ones, we're just dealing with double displacement reactions. For a lot of you, probably the hardest part is actually predicting products and writing the equations, balancing the formulas, and all that stuff. So again, sometimes I'll give you the equation, so all you have to do is the stoichiometry part. But yeah, there's going to be a couple where you actually have to write the reaction out. So you need to go back and review how to do some of that. But once you've got your balanced equation, the stoichiometry itself really isn't all that bad. Again, you're going to use that stoichiometry. It's that mole-to-mole ratio. You've got to have that balanced equation. And then the only thing is, what do I need to do to get to the moles? In this case, we're going to start with molarity information, concentration, to be able to calculate the number of moles. And then usually we're doing something at the end to convert it back to grams or something else like that. If you want to do more difficult ones, you can do it with other solutions. You can do other kinds of things at that last step. Once you've got the moles, you can kind of figure out what to go from there. So there you go. Dealing with stoichiometry and solutions, precipitation reactions. It's really pretty straightforward once you get the hang of it. I hope you're having an easier time with it now than you did back in Chapter 9. Anyway, I will see you in class. Stay tuned for Part 2, by the way, which is how we deal with doing these kinds of reactions with acids and bases instead of dealing with solids. Have a good one. See you tomorrow.